Welcome to The Explainer. Today, we're diving straight into the invisible logic that literally runs our daily lives and powers our most advanced technology. We're talking about algorithms. And we're going to trace them all the way from the simplest household chores right up to the wildly complex optimizations driving modern AI. So, let's get into it.
To kick things off, let me ask you a ridiculously simple question. How do you make spaghetti? Seriously, think about it for a second. Even if you're a seasoned developer, this relatable, everyday task perfectly grounds what an algorithm actually is. Okay, let's dive into this sequence. You boil a pot of water, you add the spaghetti and let it cook, you drain the water, and then you serve it up with some sauce. If you follow that exact order, you get exactly what you want, dinner. But what if you make a logic mistake? Like imagine trying to drain the water before you even boil it. Or, just vastly undercooking the noodles. You completely ruin the final output, right? Well, that exact failure state is a perfect metaphor for a computational logic bug.
So moving from our kitchen recipe to a slightly more formal definition, an algorithm is really just a finite sequence of mathematically rigorous instructions. It takes an input, processes it through very well-defined steps, and then spits out a desired output to solve a specific problem. Just like our pasta recipe, it is simply a structured set of rules designed to get a guaranteed result.
Section 1. Recipes for Everyday Life.
Now, imagine I asked you right now, how would you count the people in a room? Just mentally walk through that task with me. You'd probably point and just increment your count, starting right from 0. 1, 2, 3, and so on. As incredibly basic as that sounds, you are actually executing a linear algorithm. It's a fundamental computational process, and it's happening right there in your head. Let's see how this builds. Say you need to find page 100 in a printed book. You could totally check one page at a time, right? Page 1. Nope. Page 2. Nope. Page 3. Still no. I mean, that linear algorithm will eventually work, but it is painfully slow. Or alternatively, you could just flip straight to the middle of the book. If you land on, say, page 150, you instantly know page 100 has to be in the first half. Boom, you just cut the entire problem in half.
And that brings us to a really fascinating historical realization. Charles Babbage famously asked way back in 1864, by what course of calculation can these results be arrived at by the machine in the shortest time? I love that quote because it perfectly pivots us away from just basic human logic straight into the absolute core tension of computer science, efficiency and speed.
Section 2. Computers and Massive Scale. Processing the Billions.
When we think about tech giants today, your Googles, your Facebooks, they aren't searching through some 300-page book. They are dealing with data points in the billions. And at that kind of ridiculous, mind-bending scale, a slow algorithm would literally take thousands of years to run, even on the absolute fastest supercomputers. So we absolutely need heavily optimized algorithms just to survive at this scale. So the absolutely crucial point here is why this efficiency matters so much. Well, an efficient algorithm solves massive computational problems quickly. It saves physical processing time. It conserves limited computer memory space. And, perhaps most importantly right now, it literally forms the building blocks for modern AI. We actually measure this efficiency in terms of time complexity and space complexity, which is basically just a fancy way of saying how long does it take and how much memory does it eat up while it's doing the work.
Section 3. The greedy choice. Locally optimal moves.
And this brilliantly illustrates what we call the greedy approach. Think about having to make 99 cents and change. Instinctively, you're going to pick the biggest coins first, right? So 3 quarters, then 2 dimes, then 4 pennies. You don't sit there and map out every single possible coin combination in your head. No way. You just make the greedy choice. You take the biggest, best option available to you right at that exact moment. That's a strategy of making locally optimal choices, essentially hoping they magically lead to a global optimum.
Take a look at the activity selection problem we're showing here. Imagine you're trying to fit as many of these different events into your schedule as humanly possible. Well, the surprisingly optimal greedy strategy is to just always pick the activity that ends the soonest. By locally minimizing the end time for every single stack, you maximize your remaining free time for all the other events. It's fast, it's super simple, and it's often very effective.
But here is the catch. While a greedy algorithm is incredibly fast and super easy to implement, it can totally get stuck. Because it's only looking at the immediate best choice, that local optimum, it might completely miss the absolute best overall solution, the global optimum. Like, for example, if you try using a greedy algorithm to make change in a country with really weird non-standard coin values, you might actually end up handing over way more coins than mathematically necessary. So, yeah, it can be a bit short-sighted.
Section 4.
Dynamic Programming Mastery. Reusing past solutions.
Now, what's really interesting about this slide is how the dynamic programming schematic shows these overlapping subproblems. Dynamic programming basically takes a massive, intimidating problem, breaks it down, solves these overlapping smaller subproblems, and, okay, here is the absolute magic part, it stores those results in memory. It caches them. Because it remembers its past answers, it literally never has to do the same redundant work twice.
Let's just directly contrast these two methods side by side. On one hand, you have the greedy approach. It makes locally optimal choices, it is super fast to write, but it doesn't reuse solutions and it absolutely might not give you the best answer overall. Then on the other hand, we have dynamic programming. This solves overlapping subproblems, it actually reuses past solutions from its memory cache, and it guarantees you hit that global optimum. It's honestly like doing a massive, complex puzzle, but remembering exactly how you solved similar sections before, which vastly speeds up the whole shebang.
Section 5. The Future of Efficiency. Real-World Algorithms.
You know, these optimization strategies, they aren't just dry academic theory. They are actively powering your daily life. Right now, algorithms are routing your navigation apps through live traffic by calculating the shortest paths completely on the fly. They are literally sequencing the human genome. They're optimizing airline crew assignments to save companies millions of dollars. And they're directing data packets through massive global networks. Whether they're greedy or dynamic, these incredibly efficient step-by-step instructions are essentially what makes sense of the absolute massive chaos of our modern world.
Which ultimately brings us right back to you. We've just seen how unbelievably powerful algorithmic efficiency really is, right? From just finding a simple page in a book, all the way to navigating crazy city traffic. So I want to leave you with this provocative thought. What human tasks in your own everyday life are you completely overcomplicating because you aren't using an optimized algorithm? Just think about your morning routine for a second. Are you using a painfully slow linear approach, or is it finally time to implement some dynamic programming into your day? Thanks so much for joining me on this explainer, and as always, stay curious.